In this unit, we introduce a fundamental data structure called stack. The unit begins with the description of inherent characteristics of stack data structure and associated operations that can be performed on it. The working of fundamental operations is illustrated with the aid of visual presentations and animation. The unit describes how a stack can be implemented using array and linked list. Besides, the performance issues relating to different implementations are elaborated. The unit concludes with a detailed description of stack applications in computer science and other disciplines. Objectives. On completion of the unit, you should be able to define a stack and its characteristics, describe basic operations of push and pop and the associated conditions for their applicability, implement a stack using static and dynamic allocation of memory, compare the relative performance of each implementation, describe how stacks can be used in different applications, understand the use of stacks for parsing of character strings, distinguish between infix, prefix and postfix notations used to represent algebraic expressions. Explain how stack can be used to convert infix expressions into postfix notation. Understand the algorithm for evaluating arithmetical expressions with the aid of stack. Describe how stacks can be used for implementing subprograms calls. Understand the role of stack in recursive function calls. Introduction to stacks. A stack is an ordered collection of homogeneous data items in which addition of new items and removal of existing elements can take place at one end. The entry or exit point is referred to as top. The operation of adding an item to a stack is called push, and that of removing an existing item is called pop. Clearly, a stack is a dynamic data collection which work on the principle that an item added last is removed first. For this reason, a stack is also known as last in, first out, LIFO data structure. A stack has analogy with some special arrangements of certain objects used in our daily life. Familiar examples are piles of trays in a self-service cafeteria, stack of plates on a dining table, bundles of office files in in-out trays, and arrangements of letters in mailboxes. In each case, the object at top is accessed first by any user. It does not make sense to pull out an object from the middle or bottom of the pile. Let us look at a simple example to understand the working of a stack. Figure shows three states of a stack, which stores a set of alphabets. First figure shows the state with four elements A, B, C, D, with D at the top. Second figure shows the state after D has been popped off the stack. Last one indicates the state after E has been pushed onto the stack. Note that a stack data structure has some distinct features. First, it is collection of homogeneous items. This means that all data items must be of the same type and size. The elements may not necessarily be of the primitive types. These can even be complex data structure like records. Second, the elements in a stack are ordered, which implies that data are stored in certain sequence, which is determined by the frequency of insertion and deletion. The order is not visible to the user. Third, a user cannot have a direct access to an item except one at the top. A user, for instance, cannot retrieve an item from the middle or bottom of stack collection. Finally, in principle, A stack can hold any number of items. However, in practice, there is always an upper limit to stack size due to limitation of available memory in the computer. Operations on stacks. We have already mentioned the two basic operations, which involves addition and deletion of data items stored in a stack. In standard terminology, these operations are called push and pop. There are other auxiliary operations which are sometimes useful in manipulating stacks. These are referred to as isEmpty, isFull, and getTop. Let us explore these operations and examine the circumstances for their applicability. Push operation. The push operation inserts or pushes a new data element onto the stack. In certain implementations, there is a restriction on the number of items that can be added to the stack. In this situation, prior to executing the push operation, it must be checked if stack can accommodate a new item. Pop operation. The pop operation removes an existing item from the top of stack. To avoid error condition, before applying the pop operation, it must be ensured that the stack is not empty. GetTop operation. The getTop operation returns a copy of the data item at the top of the stack. The item itself is not removed from the stack. This operation is sometimes called peek. isEmpty operation. The isEmpty operation returns true if the stack contains no element and false otherwise. It is normally applied before pop operation to avoid stack underflow condition. isFull operation. The isFull operation returns true if the stack is full and cannot accommodate new items. Otherwise, false is returned. This operation is usually performed before the push operation to avoid stack overflow condition. It is not used when a stack is implemented using dynamic allocations of the storage, since space is automatically provided out of heap memory for any new entries in the stack. In addition to data manipulation operations, all applications invariably need the operations for creation and destruction of stack objects, which are called create stack and destroy stack. The create stack operation creates an empty stack. The operation is normally used at the beginning in any application using stack. The actual implementation determines how the stack is initialized at the time of creation. The destroy stack operation removes all elements from the stack and releases the memory space previously allocated to the stack data structure. Stack implementation. You would recall that implementation of an abstract data type involves developing necessary code for the associated methods and data objects. The ADT provides the framework for the implementation in the shape of an interface. In the context of a stack, essentially two schemes for the implementations are followed. These are called array-based and linked list-based implementations. The latter is also known as pointer or reference-based implementation. We now look at these schemes in a greater detail using C++ classes. The code fragment is shown on the screen. Array-based implementation of stack. In this approach, an array of appropriate data type or data structure is used to hold the elements of a stack. The declared size of array determines the maximum number of elements that can be accommodated in the stack. A variable top is used to identify the element on top of the stack. It is initialized to -1 to indicate an empty stack. The elements of stack are placed in a sequential order in the consecutive cells of an array. By convention, the first element that enters in the stack is placed in the first cell, the second in the next cell, and so forth. When an element is pushed onto stack, the value of variable top is incremented by 1. An incoming element is placed in the array cell with new index top. Likewise, when an element is popped off the stack, the array cell currently identified by top is accessed and returned, and top is decremented by 1. An array representation of stack is shown on screen, which can hold 10 stack items. Initially, the stack contains 4 elements A, B, C, and D. The variable top holds the index value 3. When item is removed, the index value is decreased to 2. Figure also shows the empty and full states of the stack. Note that after an element is popped off the stack, only the variable top is decremented. The element may stay in the array as it would be overwritten when a new element is added. Thus, the value held by variable top rather than occupation of array cell determines the current status of the stack. This is more clearly shown in this figure, which represents an empty stack even though all the cells are shown to be occupied by previously removed elements. For example, if a new element K is pushed onto the stack, it would overwrite the element A in any cell with index 0. Of course, in a particular implementation, the cell can be initialized to null value if an item is removed. This would amount to extra work with no additional gain. Linked list implementation of stack. The array-based implementation is simple and straightforward. However, it suffers from a serious drawback. The size of the stack array needs to be specified at compile time. Generally, a fixed upper bound for the ultimate expected size of stack is assumed. If an application requires much less space than a maximum size, a lot of memory space would be wasted. On the other hand, if at runtime the storage requirement exceeds the size of stack array, the application would crash. Thus, array implementation is not suitable in circumstances where stack size cannot be predicted in advance. The linked list implementation provides a better alternative solution. In the linked list design, the stack elements are stored using nodes and pointers. An example of linked representation is shown on screen. Stack stores characters A, B, C, D with D at the top. The list header pointer top points to the top element in the stack. Internally, the elements of stack are linked together using pointers. The bottom element contains null pointer. The list-based implementation has the advantage that stack can grow or shrink according to application needs. Various stack operations are performed on the front element of the list. The push method simply adds a new front node. The details of procedures for adding a node to the linked list were discussed in previous unit. Briefly, to insert an item to the front of the list, following steps are followed. Number 1. Create a new node. Number 2. Copy new element into the node. Number 3. Assign pointer of new node to point to the element next to the top. Number 4. Assign existing top pointer to the new node. Figure shows the process of pushing an element E to the stack. The pop is implemented as to remove the front element of the linked list. The steps are summarized as followed. Number 1. Copy the contents of the front element into a variable which is to return the popped value. Number 2. Assign a new pointer to the top pointer. Number 3. Set top to point to next element in the list. Number 4. Delete the node. This figure shows pictorially the steps involved in the popping operation. The isEmpty method simply checks whether or not the head pointer to the list is set to null. The getTop simply copies and returns the content of the front node. The node is not removed. Performance of stack implementation. We have seen that array implementation of a stack is simple, short, and efficient. It provides direct access to the topmost element in array. The array implementation is most suitable for applications involving a small number of stack elements of known size. By contrast, the linked list implementation is more complex. It involves creation and deletion of front node in the list. Additionally, data is either copied or removed from a node using pointers. The list-based representation is preferable when the size of a stack is totally unpredictable. In both implementations, the amount of storage space is directly proportional to the number of elements in the stack. Thus, in big O notation, the space efficiency of either implementation is O of n, where n represents total number of elements in the stack. Let us examine the time efficiency of the two implementations. In array implementation, all stack operations involved manipulation of only the topmost element in the array. Since accessing of the topmost element is independent of the number of elements in the array, the time efficiency of all stack operation is O of 1. As with array representation, the list-based implementation also involves adding or removing a single node at the front. Since probing or accessing the header node is independent of the number of nodes in the list, the operation of insertion, deletion, or checking the top element have time efficiency O of 1. The destroy operation alone has time efficiency O of n because it involves removing n nodes from the memory to release the space. The time efficiency of different stack functions for both the implementations is summarized in the table. Stack application. Stack is among the most widely used data structures. It also forms the basis of other complex and advanced data structures. Stacks are extensively used in a host of computer applications. They play a central role in program compilation and translation of high-level languages. The fundamental compilation processes, such as checking the syntax of statements and conversion of arithmetic expression for evaluation by the computer, rely heavily on the use of stacks. Stack also play a crucial role in the implementation of subroutines and function calls. Stacks are indispensable in coding of recursive procedures. Many search algorithms employ stacks to backtrack to previous states. Stacks find common use in several computer applications such as text editors, web browsers, and image manipulation softwares. Now we examine in some detail the use of stack for parsing of arithmetic expressions and their evaluation by the computer. Later, we shall briefly review some other applications. Using stack for parenthesis matching. Parentheses are often used in arithmetic expressions to specify the priority of evaluation. A pair of parentheses is also used in some programming languages such as Fortran and BASIC to enclose index of a dimensional variable. In a syntactically valid expression, each left parenthesis must match with the corresponding right parenthesis. A simple counting of left and right parentheses would not provide a correct solution. For example, this expression has same number of left and right parentheses, but it is obviously illegal. We can use a stack to validate an expression by checking that for each left parenthesis there is a right parenthesis in the correct position. Here is the algorithm. Number 1. Scan the expression from left to right. Number 2. If a left parenthesis is encountered, push it onto the stack. Number 3. When a right parenthesis is found, pop the stack. If stack is empty, report a mismatched right parenthesis. Otherwise, pop the stack and discard popped left parenthesis. Number 4. At the end of scan, if stack is not empty, report an error. This algorithm can also be used for matching other symbols such as curly braces and square brackets. Recall, braces are used in Java and C, C++ to enclose a group of statements. Conversion of infix expression to postfix notation. We now examine how a stack is used by the computer to evaluate an arithmetic expression. In a high-level language, an arithmetic expression consists of variables and constants called operands and symbols for arithmetic operations. By convention, these operations have the following order of precedence. Number 1. Exponentiations are performed first. Number 2. Division and multiplication are performed next. Number 3. Addition and subtraction are performed last. Number 4. When two operators of the same precedence appear consecutively, evaluation takes from left to right. Number 5. Parentheses may be used to enhance the level of precedence. Examples of simple arithmetic expressions are a plus b, a minus b, a static b, a slash b, and so on. The algebraic notation for arithmetic expression is called infix notation. In this notation, an operator is placed between a pair of operands. The infix notation is not suitable for computer evaluation. To simplify the processing steps, two alternative representations are used, which are called prefix and postfix notation. In the prefix notation, the operator symbol is placed before the operands. For example, the infix expressions are written in prefix notations as shown. The prefix representation is also called Polish notation in honor to its inventor, Polish mathematician John Lukowicz. A complex arithmetic expression can be converted to prefix notation by processing the brackets and operators in order of their priority. For convenience, square brackets may be used to indicate partial conversions. Here is an example. In another notation called postfix or reverse Polish notation, the operator symbol is placed after the operands. For example, the infix expressions are written in postfix notations as with the prefix representation, the infix expression can be converted step by step by partially converting the operators and brackets according to their precedence. For example, this infix expression is translated to postfix as follows. Notice that postfix expression has following features. Number 1. All operands have the same order as in the infix expression. Number 2. Parentheses are not required. Number 3. Postfix expression is not the reverse of its equivalent prefix expression. Visual conversion of infix expression to postfix notation is awkward and prone to errors. A better way is to use stack for intermediate or partial conversion. To this end, we can use an algorithm which is based on the observation that in postfix expression the operators maintain their order and that operators of higher precedence should be evaluated first. Also, since left and right parentheses are not required in the postfix representation, these should be discarded after partial processing. The conversion algorithm consists of following steps. Number 1. Scan the infix expression from left to right. Number 2. When an operand is encountered, append it to the output string for postfix representation. Number 3. Push each left parenthesis onto the stack. Number 4. When an operator is encountered, check if stack is empty. If so, push it onto the stack. Otherwise, pop operator of the greater or equal precedence from the stack and append it to the postfix output string. Continue popping until either left parenthesis is encountered or an operator of lower precedence is at the top or stack is empty. Number 5. When right parenthesis is encountered, pop off the stack and append the popped operator to the end of output string. Continue with this process until a matching left parenthesis is encountered, which should also be popped and discarded. Push the new operator onto stack. Number 6. When the scanning process is complete, pop off all operators from stack and append them to the output string. The algorithm appears to be overwhelming for manual conversions. It is, however, better suited for machine conversion. To understand the working of algorithm, consider the conversion of following infix expression. In this expression, caret symbol indicates exponentiation. The conversion steps are as shown on screen. Notice that up to step 8, all operands are appended to the output and operators are pushed onto stack. At step 9, right parenthesis is encountered and as consequence, minus and left parentheses are popped. The minus operator is popped and left parenthesis is discarded. At step 10, slash is encountered. As a result, asterisk, which has the same priority as slash, is popped and appended to the output, and slash is pushed to the stack. At step 12, plus is encountered, which has lower priority than slash in the stack. Thus, slash and plus of equal priority are popped and appended to the output, and new plus is pushed to the stack. At step 14, caret is encountered, which has higher priority than plus in the stack. It is therefore pushed to the stack. At step 15, the scanning of infix expression is complete, and therefore plus, caret, currently in stack are popped off and appended to the output. In this way, the infix expression is converted to postfix expression. Evaluation of arithmetic expression using stack. We have stated before that arithmetic expressions in algebraic notation are not suitable for evaluation by the computer. Generally, an expression in infixed representation is evaluated in two steps. First, it is converted into an equivalent postfix expression by using the algorithm previously explained. Next, the variables in the postfix expressions are replaced by their current values. Finally, the postfix expressions with numerical operands is evaluated. The last evaluation is carried out using stack to save the intermediate results. The algorithm for computation involves following steps. Number 1. The arithmetic expression in postfix notation is scanned from left to right. Number 2. If a numeral is encountered, it is pushed onto the stack. Number 3. If an operator is encountered, two operands are popped off the stack and the current operators is applied to the operands. Number 4. The result is pushed onto the stack. Consider, for example, the infix arithmetic expression. In postfix notation, it is written as: using the previous evaluation algorithm, the postfix expression is processed. The evaluation steps are depicted in figure. Use of stack in function calls. A stack plays a pivotal role in the execution of function calls. When a function is invoked, program control is transferred to entry address of the called function. After the function has been executed, the control is transferred to the next instruction in the calling program. The function calls can be nested, which means that a function can, in turn, call another function. In this process, the system must remember the addresses where to backtrack after the call function has been executed. Therefore, the return addresses and the local variables must be saved and retrieved in the reverse order. This task can be performed most efficiently with the aid of a stack. When a program or function calls another function, its arguments, the return address, and values held by the local variables are pushed onto the stack. After the call function is executed, the saved data is popped off the stack and control is transferred to the popped address. A data structure that holds the function parameters, local variables, and the return address is commonly known as stack frame. Almost all compilers for high-level programming languages make use of stack frames to process function and subroutine calls. An example of function calls and working of stack frame is shown in the figure. The function main calls a function alpha. The function alpha in turn invokes function beta. After beta has executed, the control is transferred back to alpha. When alpha has been executed, the control is transferred to main. At each stage, the value passed as arguments to the function, its address, and values of local variables are preserved in the stack frames. On backtracking, these are popped off the stack frames and returned to the calling function. Use of stack in recursive procedures. A procedure in which a function calls itself is called recursion. It is a powerful technique which is extensively used in concise description or solution of a problem. For a recursive procedure to be useful, it must satisfy two conditions. First, each procedure call should bring it closer to the solution. Second, there must be a decision point at which the procedure should terminate. A recursive procedure that satisfies these conditions is said to be well-defined. Since a recursive procedure is generally implemented in 3 steps, which are known as prologue, body, and epilogue. In the prologue step, the function arguments, local variables, and return addresses are saved by pushing them onto a stack. In the body step, a base criteria is used to determine whether or not the recursion should terminate. If so, the epilogue step and prologue step is invoked again. In the epilogue step, saved parameters, local variables, and addresses are popped off the stack and used to perform the intermediate computations. A simple example of a recursive procedure is the evaluation of a factorial. You would recall that the product of successive positive integers is called factorial. Consider, for example, the evaluation of the function factorial of n. If n equals 4, the recursive steps would be as: by backtracking the above steps, we can obtain the value of factorial of 4. An example of C++ function that can be called recursively to compute factorial of a given number is as shown. Use of stack in application software. Stacks are commonly used in the implementation of several application packages, current generation of desktop, applications such as word processing, spreadsheets, graphics, and image processing include feature to cancel any previous processing steps. In word processing, for example, any changes to a currently open document are pushed onto the stack. When the undo option is exercised, the changes are popped off the stack and applied to the current version to revert to the old version of the document. The web browser frequently uses stack to maintain a history of visited sites or downloaded web pages. As the web pages arrive, they are pushed onto the stack. Later, if a user clicks the back button, the stack is popped off to display the most recently downloaded page. In the same way, the browser can retrieve the most recently visited sites. Stack machines. Because of their frequent use in several computer science disciplines such as compilers, interpreters, and operating systems, stacks are increasingly being implemented in the hardware architecture. Originally, this facility was built into mini-computers such as PDP-2 and Burrow 5000. For this reason, these computers were commonly referred to as stack machines. Currently, most CPUs, such as Intel and Motorola processors, have built-in features for stack. The instruction set for these processors include push and pop mechanism. A push instruction causes the contents of specified memory location to be saved in the stack register. The pop instruction removes the top entry in the stack register and places in the main memory. Some microcontroller used in industrial commercial applications also employ stack for rapid processing of data in real time.